Okay, in this video, we're going to be doing Calc BC Problem Set number 22. The problems and the playlists are in the description below. Let's take a look. Number 1, given dy dx is 8x, quantity y minus 2, and we're going to let y equals f of x be the particular solution with f of 1 equals negative 1. All right, so it goes through 1, negative 1. Approximate f of 2 using Euler's method with 2 steps of equal size. I think this might be the first Euler's method problem that we've done in these problem sets. What I'm going to do universally is set up a table. The columns are going to be the x-coordinate, the y-coordinate, and then dy, the approximate change in y. And that's always going to be the derivative evaluated at the point that's kind of in the row, and then times delta x. If you're going to forget anything, it's going to be delta x, like for sure. So then I will fill in like x is equal to 1. We're going from 1 to 2, and we're using 2 equal step sizes. So like delta x is just b minus a divided by n. So it's 2 minus 1 divided by 2. So that's 1/2. So you can fill in the x column right away without like doing the problem. You should always get the x column correct. For y, we're going to start out with the given, which is negative 1. Now we have to calculate the approximate change in y that we're basically using like a tangent line at this point. So we're going to evaluate the derivative at 1, negative 1. But importantly, so you don't forget it, do delta x first, right? So it was positive 1/2. Then we evaluate the derivative. So you get 8 times 1 is 8, and then you get negative 1 minus 2. So this overall will give us negative 12. To get a new y, we take our current y, which is negative 1, and we add our approximate change. So it's negative 1 plus negative 12, negative 13. Then we just keep doing this. Sometimes they get messy, sometimes they don't. This one is crazy. I mean, the solution must be pretty close to like a vertical asymptote or something, or it's like the answer is going off to infinity because this is going to get big. So delta x. Now you take the x value, which is 3/2. So you do 8 times 3/2, which is 8 times 3/2. So that's 4 times 3, so 12. And then you take negative 13, you plug it in, that's negative 15. You do the math on this, it's 6 times negative 15 is negative 90. So to get a new y, we take our current y, which is negative 13, and we add negative 90 to get negative 103. Now, there's one last step on these, and it's really important. You have to say that the value of the function is approximately this. So f of 2 is approximately negative 103, which is like a really negative value. Often these, like if you start at negative 1, you're going to end at like negative 2, but not this case. All right, let's look at the next thing. I think what we're doing is like approximating a couple of different ways. So here we're not approximating, we're going to solve this thing. All right, let's solve it, right? So this is going to be separable. So I'm going to color code, and then I'm going to separate. So in this case, if it was like y minus 2 to the 5th, I would write, I think that was in the previous problem set, right? It was like y minus 2 to the negative 5th because that's how we integrate. But here, dy over y minus 2, that's just going to give us a natural log. So I'm going to write it the way it is. Integral signs, and then we integrate. So on the left, we get natural log absolute value of y minus 2. On the right, we're going to get 4x squared plus c. C goes on the side with the independent variable. If y is inside the natural log, you should exponentiate before you solve for c. It will solve the problem of what to do with the absolute value and like how do I choose what c value. So always exponentiate first if y is inside the natural log. So we get this. That's a new value of c, so I've changed the color. I really don't care about that. Like in my own personal work, I would just keep calling that c until I solve for it. Some people do care, so I'm changing the color just so you can, see that it happened. At this point, it's never going to really be easier to solve, so I'm going to solve for c. So we know that we're at the point 1, negative 1. We just plug in, right? And you get negative 3 is equal to c e to the 4th, which is annoying. So c is negative 3 over e to the 4th, or negative 3 e to the negative 4th. All right, we take the value of c, and we take our general solution, and we're going to sub in. So we get y minus 2 is negative 3 e to the negative 4th, e to the 4x squared, and then you have the same base and you're multiplying so you can add the exponents, so you can rewrite this as 2 minus 3 e to the 4x squared minus 4, which I think is a move that you should make, but it doesn't really change the answer. But like on a multiple choice thing, I would not expect to see the non-simplified one. I would expect to see the simplified. All right, B. Nope, C. Let's do C. Write the second degree Taylor polynomial. So we need the value of the function, the value of the first derivative, the value of the second derivative. So the value of the function is given, right? F of 1 is equal to negative 1. The derivative, so f prime of 1 is going to be dy dx evaluated at the point that we know, right, which is 1, -1. So that's going to just give us 8 times -3, which is -24. To find the value of the second derivative, we're going to need the derivative of dy dx. So this is implicit differentiation. So here's your notation. I always just read that as the second derivative. First is 8x. Derivative of y minus 2 is dy dx. And then plus, because we're doing the product rule, second, which is y minus 2, derivative of 8x is just 8, because 8 is the independent variable. And now we have to sub into this. So f double prime of 1 will be the second derivative, again evaluated at our point, which is 1, -1. But remember, at 1, -1, we now know dy dx is -24. So we're going to sub -24 in for dy dx. So we get 8 times -24 plus -3 times 8, which is -192 minus 24, or -216. All right, so we've got our values, and now we just use the formula for Taylor's formula for Taylor polynomials that we have memorized. You're going to use it so much, like if you don't have it memorized, things are going to be really rough. But it's a nice pattern. So f of x is approximately the value of the function, which is -1, and then plus the first derivative, x minus 1 to the first over 1 factorial, which some people don't write to the first and over 1 factorial. Just like when the coefficient is 0, I write it because I don't want to screw up the pattern. Plus the second derivative, and then to the second over 2 factorial. So we get this. A really common thing that I see people forget is the center, right? So they won't write x minus 1, they'll just write x, which is tough to catch, honestly. But if you are asked to approximate something, you will immediately know, because it'll be like wildly inaccurate. I'm going to leave my answer like this because generally speaking, you do not simplify these beyond this point. The only time I would is, I don't know, if I had to use it by hand, or if I was matching a multiple choice answer, or if my teacher said simplify, then I would definitely do it. What you almost never do, like never, I'm not even going to say almost, you basically never will expand the x minus 1 to a power when you're dealing with a power series. You will always leave it in its factored form. All right, next up. Given that the absolute value of the fourth derivative is less than or equal to 6 for all x, and the third degree Taylor polynomial at x equals 4 gives an approximation of f of 3.8 that's approximately 2498 over 2500. I can't tell you how long I thought about how to write that sentence, and I still don't like it. It gives an approximation of, I think I should have just said, gives an approximation of 2498 over 2500 at 3.8, at x equals 3. I don't know. The question is it possible for f of 3.8 to actually equal 1? All right, so we need to know how to find error. This will be Lagrange error bound. Anytime you see like this cryptic absolute value of a derivative less than or equal to something, you're being told the value of m, right? So we know that m is equal to 6 in this case. And then we're going to have the absolute value of what we're plugging in, which is 3.8, minus the center, which is 4. Now it's going to be to the same exponent as the order of the derivative that we used, right, to find m. So we use the fourth derivative. That's one more than the derivatives needed to write the third degree polynomial. So third degree polynomial, you're using 4. You were given the absolute value of the fourth derivative. A lot of hints there that you're using to the fourth. 4 over 4 factorial. I regret that I centered this at 4. I don't know. I should have chosen like any other number so there weren't so many 4s hanging around. This we have to actually like work with because we need to see if the answer could be 1. So 3.8 minus 4 is 0.2, which is 1/5. I think it's always easier to use fractions on these. You might differ. And 4 factorial is 24. So 6 over 24 is 1/4. And then 5 to the 4th is 625. So we have this. So this is 1 over 2500. All right, so f of 3.8 is somewhere in between our approximation plus that number and our approximation minus that number. Since we're being asked if it's bigger, if possible for it to be like a bigger number, we're just going to add and see what happens. So f of 3.8 is definitely less than or equal to, in some magical scenario, it's like never really equal. I mean, I'm saying that, but I guess it could be. So our approximation plus our potential error bound. And then this just gives us 2499 over 2500. That is less than 1, which means you can never get to 1. So this is like kind of an interesting question, right? Like you would think like, I don't know what you would think. I like that question. Next up. Evaluate the integral from -1 to 1. So I see those bounds and I think, oh, it's probably like an even function or an odd function, gonna like help us out. Not the case. This function is neither even nor odd, so we just have to like do it. X squared e to the -2x dx. So I'm doing integration by parts. So I'm gonna just color code it here. I'm gonna make u equal x squared, dv is everything that's left, e to the -2x dx. Set it up, we got u, v, and then we have the sign that's gonna go between things. For u, we take derivatives, so it's going to be x squared, start at u, and then the derivative. If we go again, we'll get 0, and 0 times anything is 0, so we know we're done. In the v column, we have to integrate, right? So we know dv is e to the -2x dx, so we have to find v and then keep integrating. So v is going to be -1/2 e to the -2x. And then integrate that, and you get +1/4 e to the -2x. And then integrate that, you get -1/8 e to the -2x. So you keep getting like a power of 2 in the denominator there, like because you keep putting another 1/2 in when you integrate every time. And then the signs always just go minus plus, and then it'll keep going minus plus minus plus. Doesn't mean your final answer will do that, because it's possible that the product of u times v will be positive or negative and kind of like mess things up, which actually happens in this case, right? So it's uv, which is -1/2 x squared e to the -2x, and then minus. And then it's uv, which is going to be 2 times 1/4, so 1/2, and then x e to the -2x. And then plus uv, so 2 times -1/8 is -1/4. So I'll put that in parentheses, just, you don't want to write plus minus. That'd be weird. So we get this. I'm putting plus c, but we're actually doing a definite integral. So what I'm going to do now is just fundamental theorem this, right? So -1 to 1 of x squared e to the -2x. We take our antiderivative, which I'm going to factor 1/2 e to the -2x out of. I think it just looks a little cleaner. It certainly makes it easier to like sub in for everything. We're left with a -x squared, a minus x, and a -1/2. And we're going from -1 to 1, and there's nothing to take advantage of. So, I don't know, we'll just do it, right? We'll get 1/2 e to the -2nd, and then this is when we plug in 1. Get this, minus, plug in -1, you get 1/2 e to the +2nd, and then you get -1 + 1 -1/2. So that cleans up nicely. This answer is just gross. I mean, there's nothing really nice about it. 1/2 e to the -2nd, -5/2, and then minus 1/2 e to the 2nd times -1/2. So overall, we get -5/4 e to the -2nd plus 1/4 e to the +2nd. And that's the answer. All right. That's the little problem set. I hope this was helpful, and good luck.